we have no idea how unique we are, because how unique we assume we are affects how unique we end up.
We're groping our way towards an answer, I would say.
Welcome to Bad Astra. Today, we will be updating you on the progress of the start of the United Federation of Planets. Nora Bailey, a PhD candidate at the University of Chicago, is here to talk about her work in exoplanets and the search for Spock. Hi, Nora. How close are we to finding Vulcan?
Hi. So, I don't know if you know this, but exoplanets is about more than just looking for aliens. That's not at all what I do. There may have been a mix-up.
It's also about establishing Earth colonies so we can be ready for the coming intergalactic war.
Yeah, kind of, I guess. But, some exoplanet scientists are looking for signs of life, but it's more, little green bacteria rather than little green men. And we're certainly not planning on going there anytime soon. Sorry.
Not building starships?
I mean, we can build them. They just won't get there. Space is big. I don't know if you know that, but it's real big.
But what if we jump to hyperspace or warp? I think I used the wrong franchise there.
Well, I'm not an expert in warp drive, so I guess I can't speak to that.
Okay, so if you're not looking for aliens, and even the aliens you are looking for are bacteria, what do you actually do?
Well, what do I actually do? I do something completely different. I study the dynamics of exoplanets. So that's just how planets and other systems move under the force of gravity, which might sound simple, but actually is pretty complicated.
You use math to figure out how planets orbit other stars that aren't the sun.
Yep, absolutely. All of my work is done on a computer. I use simulations to probe systems and explore how they interact.
Can you tell me more about what the field of exoplanets is actually? Like, obviously, this isn't Star Trek. What are you actually looking for?
It's not Star Trek, but it's still pretty freaking cool if you ask me. So the very first exoplanet around a sun-like star was detected back in 1992. I was actually alive when the first exoplanet around a star was discovered. So to have it come this far in just my lifetime, now we've detected over 4,000 confirmed exoplanets, is really amazing. It's such an exciting field, and there's so many different aspects of it. So there are people that actually detect these planets, which is really hard to do because planets are very, very small and very dim compared to the stars that they orbit. So we have to come up with these really creative ways of detecting them. And so there are people that do that. There are people that are like me, that are theorists, that just kind of think about these systems and explore various possibilities related to them. Like I said, I'm a dynamicist, but there are theorists in every subfield of exoplanets. There are people that are studying what the planetary interiors would be like, or what the atmospheres would be like, how the stellar type influences the planets, the habitability of the planets. Just there's a wide variety of things that people study in relation to exoplanets.
So it's less about finding little green men and more about building a broader picture of what the galaxy is made up of.
Yes, we have learned so much that was like surprising to us. Like I said, 1992, right, is this kind of quintessential planet discovery. They actually won the Nobel Prize for this just in 2019. It was what we call a hot Jupiter. So this is basically a giant planet like Jupiter in our system, but it's very, very close to its star, which makes it very hot. So hot Jupiter. We're very creative when it comes to naming things in astronomy. But like this was an exciting new type of planet that we really didn't think existed. And it was the very first one we ever discovered because it turns out they're very easy to discover because they're so big and close to their star. So that's just one example, but pretty much every time we discover new exoplanets, we learn new things about planetary systems, how they form, what they look like throughout the galaxy, and what our solar system is like in comparison, right? We get a better context of the galaxy and of the planets in the galaxy and how our system and our little, Earth ball that we sit on fits into that.
Are we, as a solar system, would you say, unique, Are we average? Like on a scale of 1 to 10 in hotness, how would you rate our solar system?
Well, on a scale of 1 to 10 in hotness, I would rate us an 11 because we have us, and I think that makes us pretty spectacular.
Yeah, we cute.
Exactly. But actually, this is still kind of an open question of how unique is the solar system. And partly that's because some of the planets in our solar system are difficult to detect in exoplanet systems based on their size. Like, say, Mercury is so small that it's very difficult to detect planets like Mercury in other systems. Or, Jupiter is big and it's easy to detect Jupiters, but it's on a relatively, wide orbit and it takes a long time to orbit. And so when we're looking for these signals to detect planets, we have to be able to detect them over time. And so the farther out a planet is, the more time we need to observe a star. And like I said, we've only been doing this for 20, 30 years. And so we really haven't probed the kind of outer reaches of these systems yet. And so building a comprehensive picture of what a system looks like is very difficult and is very actively being worked on by a lot of people.
So the observation bias of we can detect more of this type of solar system because it's easier to detect doesn't always mean there's more of this type of solar system, even though we've detected more of it because of that survivor bias.
Exactly. So detangling these observational biases from the data is really important and it's really difficult. And so a lot of very smart people are working on that. And you also run into a problem that different methods of detecting planets kind of get at different areas of the systems that you're looking at. So we might be really complete. That's just what we say when we think that we've detected a large enough amount to understand basically what the population looks like. So we want to be very complete and close in systems. And we might be somewhat complete in far out systems based on a different type of method. But those two different types of methods are looking at different stars. So we haven't been able to put together an entire picture of systems. And so we can't say for sure whether these systems that have an inside like this and an outside like this are the same type of systems so that the entire system would look one way or the other.
Yeah, it's like how hunters wear orange because deer can't really see orange, but humans can. And so a deer looking around sees a bunch of blues and greens because that's how their eyes work. But they don't see the hunter wearing orange because the hunter just kind of looks gray. So the deer thinks everything is blue and green. But actually there's a hunter there. And in this case, I guess we're the deer and there might be an impending alien invasion.
I mean, never rule it out, but hopefully not.
That metaphor got dark. I didn't know where I was going. And
there's actually an interesting idea about this called the Dark Forest, and it's the centerpiece of a trilogy of books by a Chinese science fiction author called The Three-Body Problem. So if any of your viewers are interested in that kind of thing, I do recommend it.
And I'll put it below.
Okay.
A lot of people know, I think, that one of the most common or one of the original ways that was most publicized of detecting these planets was transits. So the planet goes in front of its star and the star's overall brightness dims a little because the planet is blocking out some of that starlight. That's why it's way easier to detect the hot Jupiters because they're transiting and they block out more starlight. Would that lead to an issue of detecting planets orbiting in a different plane? If they cross in a plane like this and the star's here, they'll cross around. But what if they're going around like what if they're going around like this and never cross in front of the star? Like, is that another type of observational bias you have to deal with, or are there other ways of detecting those kinds of planets?
Yeah, so that's definitely a consideration with transits. So this isn't necessarily an issue doing kind of these statistics because we would assume, looking out in the universe at our galaxy, the orbits are going to be oriented randomly to us, right? So even if we're only seeing the small band of planets that happen to be transiting a star, we expect that would be similar to the other orientations because that's just randomized. But where this really becomes an issue is looking at planets within the same system. Because now that system, we have seen a planet that's transiting, but because the band basically at which, we would see a transit is very narrow, and it's actually harder the farther out you are out from the star. So planets that are more distant from their star are less likely to transit. And even a very small difference in kind of the angle between the planets can cause these outer planets to not transit. Yeah. Or if you have some sort of even not necessarily an outer planet, but maybe an inner planet that for some reason just has a slightly larger angle away from the rest of the planets, it might be missed. So kind of doing these intra-system calculations is really where that kind of transit bias becomes a big issue. And it's actually perhaps partially responsible for something that we call the Kepler dichotomy, which is basically that in the Kepler sample, so Kepler was a mission that observed hundreds of thousands of stars and detected thousands of exoplanets. And we kind of see two separate populations where there's this kind of increased number of single planet systems within the data than we would expect. And so this might be because we're only seeing one planet that's happened to be transiting, and there are actually other planets in that system, but they're just not actually crossing that plane of the sky that we can see. So yeah, it's definitely something that needs to be taken into account.
Yeah, and also because this field is so new and the Kepler survey was only so much time, Earth has a 1 year 1 year orbit, so every year it transits once. But I know like Jupiter, Saturn, Neptune, Uranus, like they all take way longer to transit. So don't you kind of have to get lucky that you see that transit unless you're looking at it for hundreds of years?
Yeah, exactly. And this kind of goes back to what I was saying before about how it's difficult to detect planets in the outer parts of the system. And that's one of the reasons. So you need to see a certain number of transits to kind of know there's a planet there. If you just see a single transit, you really don't get that much information. And so, yeah, the Kepler survey was about 3.5 to 4 years. And so you might be able to get planets, out to that length, but you wouldn't be probing the Jupiters and the Saturns of these other systems.
So that's a really difficult problem because you have to normalize for that. But then if you normalize based on what we know about our own solar system, you're incorporating that statistical bias because we might be really unique. So we have no idea how unique we are because how unique we assume we are affects how unique we end up.
We're groping our way towards an answer, I would say. There are some aspects of our system that we can say is or is not normal or unique. For example, the most common type of planet out there seems to be these planets that we call super Earths, which are basically kind of, like I said, creative naming. So super Earths are just bigger than Earth, these kind of bigger sized Earth. And we don't have any of these in our solar system, but they seem to be very common throughout the galaxy. And so in this way, we are a little bit unique that we don't have a super Earth in our system. Well, potentially Planet 9, but
I think our Earth is pretty super.
I think so too. I agree. So yeah, so in some ways like that, we can say, we are unique, or the fact that we have giant planets, giant planets aren't as common as these smaller planets. So that makes us a little bit unique. But really looking at the system as a whole and saying how unique are we is I think still a relatively open question.
So now let's zoom in a little bit from the wide field to just your research. So can you tell me about what you are currently working on, or if you just finished a project really recently, what should we know about you and your research?
I should preface this with saying is when you're doing a PhD, you're really, really narrowing in on a very, very narrow slice of a field. And it's often not the most exciting thing to people outside the field, right? So I understand that this may not sound very exciting to other people, but obviously it's very exciting to me because it's my own research. So what I have been working on recently, I have a paper that should hopefully be coming out in the next couple months on this, is looking specifically at the data from the Kepler survey and looking at these planets that are close to what we call a mean motion resonance. So mean motion resonance basically means that the periods are kind of these integer multiples of one another. So in this case, I was looking at the 3-to-1 and the 5-to-3 resonances. So that means for the 3-to-1, your inner planet goes around 3 times for every 1 time the outer planet in the pair goes around. And this leads to some interesting dynamical effects. What me and my advisor are working on is using the particular way that eccentricity affects the resonance of these planet pairs. And eccentricity is just how non-circular the orbit is. So basically, the more eccentric planet pairs are more easily caught into these resonances, which happen near these mean motion contrabilities. And
are these resonances stable? Like, does the gravitation of the system, like once you get into a 3-to-1 orbit, does it kind of stick there?
Yeah, so it can be stabilizing or destabilizing. So if it's actually in the resonance, it's actually in, which is like a kind of particular dynamical state, then it is very stable. But if it gets close to the resonance without actually getting into the resonance, that can be very destabilizing. But we do assume basically that all of the planets we observe are stable, because otherwise we would be saying we're seeing them at a very special moment in time before they disintegrated, which we don't think is likely, right?
Maybe, but probably not.
Exactly. So it's kind of a safe assumption that if we're observing a system, it's stable. We're looking at these two particular resonances and basically saying, if the planets there were eccentric, we might see this kind of increase in the peak near this resonance, because these more eccentric planets are basically more easily caught into resonance. And we don't actually see this. And so we use this method to basically place a limit on how eccentric we think these planet pairs. This has been done by other methods before. And so this is just kind of a complementary method that has, different kind of biases and assumptions built into it. So all of these kind of different methods that we use help us really become more certain that we actually do think, the Kepler planets have pretty low eccentricities in general.
That is just kind of you coming at the problem from a different direction than another paper and hoping that you arrive at the same conclusion, because that means that both of you are coming from different biases have canceled out your biases correctly.
Yep. Hopefully.
Again, we're groping in the dark for answers.
Yes.
Quite literally, space is very dark. So these must be really close in planets if Kepler is determined, has captured 3 transits for one planet and at least one transit for another planet, and determined that that's stable. Like how?
Yeah, these are relatively compact systems. The inner planet on at least one that I'm thinking of has about a 5-day period, and some of them are out to like maybe 100 or something days. But yeah, these are compact systems.
Yeah. So the planets are really close to their stars. They're orbiting really fast. A year is like a week.
Yes. Yeah, exactly. And that's actually kind of central to what we're trying to do, because the signature that we're looking for, this very like narrow spike near the resonance, actually is a lot easier to see when you can time average over these cycles that happen. Not the period cycle, but what was called a libration cycle. And so because these planets have orbited so many times and we observe them in Kepler that has this, multi-year time involved, then we would see this signal if it was there, basically.
So where theory meets observations, you're testing to see, are your simulations correct?
Yep.
Cool. That was probably about as much math and science. I have my daily dose of science, and I still have about 20 minutes of listening to my wife explain her research. I need to leave enough room for that.
You're a good wife.
Otherwise, I ask really stupid questions. My brain's just done. So she'll be going, and I'll ask like these good questions, and I'll hit my limit. I'll be like, so dinner.
I mean, dinner is pretty important. I'm having a burrito tonight, and I'm already thinking about it. So.
Okay, so now that we've hit my pre-wife limit of science, let's talk about your career path, because it's actually quite interesting. Most people who are in STEM go straight high school to college to graduate school, and you took a slightly non-traditional path. Would you like to talk about that and about how that has influenced your current PhD, your life in general?
Absolutely. So I definitely have been kind of on my own path in life. So I went to the Naval Academy for my undergraduate degree, and graduating from the Naval Academy, you're required to serve in the Navy for 5 years afterwards. So I did my 5 years in the Navy. I was mostly out in San Diego. I was a nuclear surface officer. So I worked driving ships and down in the reactor, operating the reactor basically of an aircraft carrier, which was really cool. But I decided it wasn't for me long term. And so I got out of the Navy after 5 years, and I didn't really know what I wanted to do. I wanted to stay in San Diego, though, because I love San Diego. And yeah, exactly. And so I joined a consulting firm there, and I was a project management consultant, and I was consulting with the DoD and a Navy client out there. And nothing against my clients or my firm. They were great, but I was bored out of my mind. Just like horribly bored.
I used to work in consulting too.
And it was like government consulting. And so like sometimes people hear consulting and they think, oh, you're flying to a new place every week. It's like 80-hour weeks and you're making like crazy money. That's not what this was for me. I was a government consultant. And so I was full-time on a government project in a government office. And I have a lot of respect for our government and the work they do, but it is very slow paced.
Wait, you work in academia now. Are you still going to call the government slow compared to academia?
I am. Yeah. Mm-hmm. Yeah. So I would just say I was not being mentally challenged, and and I did try and seek out opportunities at work, and it just wasn't working out. And I started daydreaming about going back to school, and it had always kind of been in the back of my head, like one of those kind of what if scenarios that like castles in the air, right? Oh, what if I went and got my PhD in exoplanets? Like, wouldn't that be cool? Because I did study astrophysics for my undergrad, but never with the intention of actually going on to grad school or continuing with it, because I knew I had to be in the Navy. It was kind of low risk what I chose to study, right? So it was like, study something I think is cool, astrophysics. I actually originally planned to study political science, which I'm so glad I didn't do. It would have been awful. But yeah, so it was like kind of just for fun that I picked astrophysics for my undergrad major. And then as I was daydreaming in my soul crushing consulting job, I started to really seriously think about it. And I did it just kind of one step at a time. So there's a lot of things to do to apply to grad school. And so instead of being like, okay, I'm just going to like completely change my life overnight, I was like, well, if I do want to go to grad school, I have to take the GRE. So I'll study for the GRE. So I studied for the GRE. And then I started studying for the physics GRE, and then, which I thought was so much fun, which I should probably tell you, I'm a huge nerd, and that was probably a sign.
I was going to say, I remember when my wife was studying for the physics GRE. Oh, she's going to hate me for saying this on the internet, but she actually broke up with me while she was studying for physics GRE. It was fine. The breakup lasted 12 hours. We're married now. So
yeah, it worked out.
it worked out. But she was very, very stressed.
I think, yeah, for me, because it was something I was choosing to do and it was optional and I was just kind of doing it for fun. I just enjoyed it. I was at coffee shops in San Diego with my Conquering the GRE physics like handbook and just working through problems and just having a blast, really. And so then I decided to take the test and I did okay on it. And so then I thought, oh, well, okay, maybe I will submit some applications. But like, I was like, I'm only going to submit to like places I would like be excited to go to, right? No like safety schools, nothing like that. And I was like, and if I get accepted, I don't have to go, right? Like this is still like a kind of maybe thing. Because I was making like decent money, right? I had a boyfriend, like I had a job. Like it was definitely not obvious to me that I was going to end up choosing this. And so, yeah, so then I applied to grad schools and for some reason, some of them let me in, which I still haven't quite figured out.
But in Chicago.
I got into a couple places and I was really, really happy. And I felt very lucky that worked out for me. And I went to some of the open houses and again, was like, if I don't like it, if I don't feel like it's going to be a good fit, I don't have to accept anything, but obviously I did. And I ended up really enjoying Chicago. I really saw myself there. And I decided to go ahead and take the plunge. And then I quit my job. And I quit my job in May of the year that I was going to start grad school. So I was back in 2017. And I spent that summer studying physics because it had been at that point 8 years since I had graduated from undergrad. And so I kind of needed to brush up. And I also learned how to code that summer. So I taught myself Python that summer. And then, September 2017, I started grad school and I'm still here. It's 2021 now, and I'm hopefully going to graduate next year. We'll see.
That is so cool. I'm thinking like that seems like a pro of taking your path is just how little stress there was. Like I am remembering like not just my wife's experience, but like all of my undergraduate friends who were applying to grad school. I had this kind of weird path where my senior year, I was getting a master's because I had decided I didn't want to go to get my PhD. I was like, grad school's great. It's not for me. But I finished my undergrad in 3 years. So I spent but I didn't want to I had already signed up for band the next year. I couldn't. So I ended up getting my master's degree. Just so many friends who were applying to grad school, applying to med school, and especially my wife, were all so nervous because this is what they wanted to do. They were applying to dozens of places, freaking out about interviews, freaking out about letters of recommendation. It just, because they thought this was their only shot, it was a huge stressor. And really the first half of everybody's senior year was colored by that, by getting into grad school or law school or med school, all of those. And the way you describe the process seems like what you want it to be. Physics, I'm going to get into this. I'm going to look for programs that really excite me. And you had this kind of safety net of, well, if I don't get in, I have a job, I have a place, I know what my life is, I can apply again.
I agree with you that it's definitely a pro. I didn't need to get into grad school. It was and whereas you're coming from undergrad, it's a lot different stakes if you're applying directly to grad school. And I think that helped me have a lot better perspective about it. But I mean, not to say that what is totally stress-free. Obviously, I was stressing at many points in the process, but it was bearable stress. It was a good kind of stress, I would say, the kind of stress that inspires you to actually do things instead of, doing nothing.
Yeah. And I also want to say, as a disclaimer, people who apply to grad school and don't get in right away, especially med school, you can apply. I have a lot of friends who purposely took a year to get experience in the field, become an EMT, go work at a clinic, and then apply later. Nora is a phenomenal example that going back to graduate school, not right out of undergrad, is not only doable, but you can get into a top tier school and it can be a better path for a lot of people.
I mean, obviously it's worked for me, but it has helped my graduate school experience, I think, because I have a lot more life experience and I have a lot more context just for things. And not to say my cohort is unexperienced, but they're a little less experienced than
your cohort.
They're just a little bit less experienced in things practical everyday things. I remember talking
on time, coming into work in the morning rather than the afternoon.
Well, and it's not even that. I mean, one of the things I love about being a grad student is it's so flexible. And after working at a job where, when I was in the Navy, I had to be there at 6:30 in the morning. And I don't do that anymore. My boyfriend now actually does not believe that I ever did that. He's like, I think you're lying to me. You never got up at 6, because I'm not a morning person. But having the experience of having a job beforehand helps me treat grad school as a job. And so I think, in undergrad, you're doing problem sets until 2 a.m, right? It's not a job, it's school, it's your whole life. And then grad school, if you take that attitude to grad school, I think it can lead to a lot of burnout.
Yeah.
Whereas where I was coming in, I came from another 9-to-5 job. And to me, this was just another job. One I liked a lot more than my last one, but paid a lot less. And so, I think it's helped me with my work-life balance. I have no problem signing off at the end of the day. I don't work on weekends, and unless I really have to. I mean, if there's something important, I'm not going to not do it. But I recognize there's always going to be more work to do, and I can just stop and be done. And I don't want to be doing problem sets at 10 p.m. at night. I'm going to go to bed at 10 p.m. I'm old.
And I really think that work-life balance is so important. I remember her first year of grad school and her second year, and it was very much college part 2, but now with more working. And there is a level of, she's now a lot better at the whole work-life balance, but it is hard coming from that, school is your whole life. Now this is grad school. It should also be your whole life. Once you get out of college, I think I very quickly learned, well, actually, no, that's not true. My first job consulting, I treated that as my whole life. It was a mistake.
But you learn from that.
And now I'm very happy in my current job. I mean, I get to do this. But I think knowing kind of how to set boundaries is something that we don't learn in undergrad. And a lot of the politics of graduate school kind of try to prevent you from learning that as well.
Yeah, grad school can be very, it's very a lot of it is very self-directed. I mean, like, obviously there's your classes and like if you're TAing or something, like that's going to be very structured, but like your general work is going to be self-directed. And so there's not going to be someone there telling you you're working too much there. And so it has to be you. And we can be very bad at that. And so I think that's something that, you know, my experience has helped me be good at. And I don't know, just being more assertive and knowing more about who I am as a person and as an adult, and not feeling so intimidated by maybe, you know, the faculty or having to deal with the staff and just things like that. There's like a certain comfort level that comes with being a little older and having a little bit more experience.
You mean being able to say no to someone who is in a position of authority over you?
Yes.
You can do. That took me a while to learn.
But I mean, there are downsides as well. Like, I am a lot older than all of pretty much everyone that I started grad school with. And so that makes it can make it harder to, you know, form friendships and like close bonds, because we're just kind of at different stages of life. And not like I dislike anyone that I go to school with, but just like we're not hanging out usually like on the weekends or anything. Coming from a job that paid relatively well and then coming into grad school and getting a grad stipend and trying to live on that can be challenging, I think, if you're already established in a career and having that expectation. Now, for me, I happen to be lucky because I tend to be a very frugal person. And because I was so unhappy in my previous job, I was very focused on saving a lot of money for retirement and for being able to get out of that job. And so it wasn't actually a big difference in lifestyle for me because I was already saving most of my money. So I was able to step back down into the like lower cost of living for a grad student, but it's certainly a pretty serious consideration. And I did a lot of math about like how much salary I was going to be missing out on by spending 5 years at grad school. And it's quite a lot, but you know, at the end of the day, I'm so much happier, and like you can't put a price on that. So
I'm making way less, but in the therapy that I'm spending so much money on therapy. I don't know why I felt the need to mathematically justify using the thing that I wanted to do, but I completely understand your like, how do I make this work?
That was something too that I considered when I was trying to decide on programs. And I think especially kind of coming into grad school, there's a lot of emphasis on like picking the right advisor and picking the right program that's going to have the connections to get you where to go. And you don't want to think about money. Like that's not the important thing, but like money is important. So like, don't be afraid to think about that. Don't be afraid to ask about it. Like definitely if you're considering grad school, like take that into consideration. So yeah, for me, like one of the big positives of UChicago was that Chicago has a lower cost of living and the stipend was very competitive. And so it has helped me, you know, be able to make this transition without having to, you know, live on ramen every night or have roommates, because I was 30 years old and I didn't want roommates. Like that was kind of a baseline criteria for me. I
can understand. That was one of our things when we moved out. Obviously, Rebecca and I were planning on still living together, but we were like, right. We don't want, of course, like saying we don't want roommates. We're still going to live with each other. It was the 5 additional people living. Yeah. That's the standard of living in college. It's like, how many people can you pack in? Like,
yeah, I like my space.
You can probably fit 3 or 4 beds in the living room. That works, right? What's the legal maximum you can have on the lease?
Before it's considered a brothel. I remember Rebecca telling me about that.
Oh, yeah, the brothel law. Oh, yeah, I lived in several brothels based on that law. So do you have any advice for people who want to study astronomy who are maybe in high school or are just starting out in college and are really wanting to go to grad school? And also, do you have advice for people who are maybe working in consulting or some other job and they want to maybe go back to school or either for astronomy or something else?
Yeah. So I guess for those that are on the more traditional path or thinking about, you know, choosing grad school, while you're in high school, I would say, one, don't stress yourself out. You're in high school, have fun. Like I actually got an email from a high school student the other day that was like asking me, they were like really concerned about, you know, getting into a program and they wanted to work with me, which I don't take on students, but I just remember thinking, you don't need to do that in high school. But I know it's very competitive to get into good colleges, but I wouldn't say there's anything you must do as a high school student that's going to like break your career or anything like that. If you think you might be interested in physics and astronomy, I highly recommend you take calculus in high school if you can, and take physics if you can, just because it will help you know if you like it. Although So I obviously studied physics in my undergrad, and I ran into my high school physics teacher. I took AP physics in high school, and I ran into him the summer after I had declared my major to be physics. And I was so excited, and I said, "Oh, you're never going to guess I chose physics as my major." And he just looked at me and he goes, "You hated my class." And it's true. And I complained about it so much. So maybe, don't judge too quickly off of your AP physics experience in high school. But it will give you an idea of what physics is like.
I remember loving my AP physics in well, although I think I really lucked out with my high school teachers. I also was such a nerd in high school.
I was too.
It's Star Trek, so nothing's changed. But I think that's good advice of taking calculus. Also, taking calculus and AP physics will set you up to spread out your physics classes.
Yes, it will help you from having to really overwhelm yourself with credits in college if you decide to major in something like that. As far as college, I guess I don't know too much about applying directly to grad school from college, so I can't necessarily speak to that. But I think that it is becoming more and more important. And I think this is a bit unfortunate, but I think that's just the way it is to actually do research as an undergrad. I personally did not do research as an undergrad. And so I think I'm probably lucky that I'm a non-traditional student, because I don't think I would have gotten it if I was a traditional student. But if you have the opportunity to do research, I definitely recommend you pursue that. It doesn't necessarily have to, result in a paper or anything like that, but just something that you can speak to on your grad school applications. And yeah, find that that part of the field that really excites you and see what you can do with that. Kind of become familiar with it, get to know who the people are in the field. And, that can help you kind of see what's out there and where you might want to go, because different schools have different strengths and different reputations and different faculties. And probably one of my number one pieces of advice is learn how to code. It is very important in pretty much every aspect of physics these days, and you will probably need to know how to do it. So definitely take advantage of your time in college to learn how to do it. I recommend Python, but it's not the only language that you can learn. But I think at least in astrophysics, that seems to be kind of the current language that people are preferring, and that's the language I use for my work.
Rebecca had to learn a little bit of Fortran.
Yeah,
she was making a Python wrapper for a thing originally written in Fortran, so she of course needed Python. But
yeah, I've run across a couple Fortran programs I had to run because they were kind of old programs that I was trying to use, but they were painful, and I don't recommend that if you can avoid it.
Definitely learn Python. Learn your way to Google your way around some random coding language.
Yeah, exactly. Stack Overflow will become your best friend. Those lovely people that spend so much time helping other people out for free.
Even if you get into consulting, coding is helpful.
Yes, it can. When I was a consultant, the number of people that thought I was an Excel whiz because I knew how to Google.
Oh, yeah.
It's kind of sad, really.
I'll write a very simple macro for that. And they're
how did you do that? And you're like, I literally Googled it. I didn't know how to do it 5 minutes ago. It's not that hard.
And then I copied and I pasted and I changed the cell names.
Yes, so very handy to have. And then I guess for other non-traditional students who are thinking about returning to school, I think the biggest advice I have is don't count yourself out. I know that I was very sure that it was too late for me. I really thought it was too late for me. And I didn't think it had been 8 years since I was an undergrad. I didn't think I was going to be able to relearn all the physics I needed to know. And I was really, really nervous about reaching out to people to write letters for me, because you need letters to get into grad school, letters of recommendation. And so I had to email some of my professors from undergrad who I hadn't talked to in 8-9 years and be like, "Hi, do you remember me? Will you write me a letter?" And I felt so stupid. Honestly, I felt stupid. And they were so happy to do it. And I think that most people will find that if you reach out to someone, they are going to be happy to help you. And it's not that big of a deal. I know it feels like a big deal, but it doesn't have to be. And so, so don't be afraid to just try that. Just reach out, just talk to people, and kind of think about it seriously, and think about what your life would look like. And if you can see yourself doing it, and if you can, then figure out the steps you need, you need this GRE or that GRE, and start working on it.
And also, if you're coming from a non-traditional path, if you don't do well in the GRE or the physics GRE this year, you can always retake them. There's
absolutely. And because you have a job,
Yeah.
It costs money to take the GRE, but it's not a very significant amount. But it's a significant amount if you're an undergrad, I think.
Yeah.
But like for me, in a real job, like, okay, it's like $100 or something. Like that probably sounds very elitist, but I just mean like it's not going to break your bank if you have to take the test twice.
Yeah. One thing we should also mention for frequent viewers of my channel or people just happening upon this interview, first of all, thank you. Come, stay a while, maybe subscribe, like, share, all the things. But Nora actually has her own channel, Nora's Guide to the Galaxy, also on YouTube. I will link it below. Nora, can you tell us a little bit about what you cover on your channel?
Yeah, absolutely. So Nora's Guide to the Galaxy, like you said, I even have merch. Like the title suggests, basically tackle astronomy topics. I put out a science video every Monday that covers a different topic in astronomy. I have a few different series, like we do an Exoplanets 101 series. Right now I'm in the middle of a alphabet-based series, so just working my way through the alphabet. I'm on the letter L now, I believe. So those come out every Monday. And then every Thursday, I do a news video that's a roundup of kind of space and astronomy news from the week. Things like what's SpaceX up to? Did the most recent Starship explode? Probably. But then also astronomy news. Like today, there was just a really exciting result that came out of Fermilab about the muon G-2. So things like that. I cover that as well. So like she said, I'm on YouTube, and then you can also find me on TikTok and Instagram and everywhere. So you
can see those links in the description below. So I do have a very final, a little bit controversial question. Do you think exoplanets are planets?
This is a really interesting question, and it's one I've actually talked about on my channel. But by the definition of exoplanets, no, exoplanets are not, because planets are only considered planets if they orbit our sun. And by definition, exoplanets do not orbit our sun. And so there's not actually an official definition for what an exoplanet is. It's kind of a, you know it when you see it type thing. So no, technically exoplanets aren't planets, but we frequently refer to them as planets in kind of everyday speech.
For those of you who don't know, I will put it up on the screen. The IAU, the International Astronomical Union, has a very specific definition of a planet. You need to hit 3 criteria. 1, the planet has to orbit around the sun. So that's why Nora has said that exoplanets aren't planets, because they don't orbit our sun. 2, the object has to have sufficient mass to assume hydrostatic equilibrium, which means it's got a nearly round shape. So planets have to be round. You can't have irregular shapes. Those are too small. And 3, which this is another sticking, the planet has to have cleared the neighborhood around its orbit. Now, how would you define clearing the neighborhood around a planet's orbit? You could say cleared it of all other bodies, cleared it of moons. If you go with a really strict interpretation, anything with a moon orbiting it is technically an additional body. It hasn't cleared its orbit, in which case only Mercury and Venus are planets. All the other planets are fake. They've got moons, so they don't meet the IAU's definition.
Well, clearing your orbit doesn't mean that you can't have a moon. It just means that it has to be the dominant body at that orbit. And so if a moon is in orbit around a planet, the planet is still quite clearly the dominant body.
So if you're saying that clear the neighborhood around its orbit just means become the dominant body in its orbit, then why didn't the IAU specify further what that means in the definition? Like, why is it so vague?
I mean, I guess I don't think it's that vague. So like I said, with exoplanets, sometimes it's a like, you know it when you see it situation. And so with anything classification based, you're kind of coming up with these categories that make sense based on what we observe. And so we observe these planets that are the dominant bodies at their orbit. And so that's what this definition is getting at.
Other question. This is more of an adjective noun English question. If dwarf stars are still stars, why aren't dwarf planets still planets?
Sure. I mean, that's not, if someone wanted to say Pluto's a planet because it's a dwarf planet, I would have no problem with that. But when people say that Pluto is not a dwarf planet, I would take issue with that.
Oh, nobody's arguing that Pluto isn't a dwarf planet. We are very dwarf planet positive. We are arguing that dwarf planets should be a type of planet in the way that dwarf stars are a type of star. No one is saying that white dwarfs don't get to be stars.
Well, it depends. That's a whole nother thing, I guess. But because white dwarfs are, the end state of a star, I think it's a separate category. There's planets, we call them major planets, and then there are dwarf planets. So Pluto is not in the major planet category.
So you would be a proponent of saying Pluto is a planet, but it's not a major planet. It's a dwarf planet.
Sure, that's one way I think of saying it. People have this attachment to the idea of Pluto as a planet because they learned that Pluto was a planet when they were children, because that was our understanding of the solar system at the time. So keep in mind the timeline here. Pluto was detected in 1930. And it was the only thing that we knew of that was, like that. And it was weird, even when we detected it. It's not in the same planet as other planets. It's very eccentric. But it was, it did kind of be like, okay, I guess it's a planet. But now, starting in the 90s, we started detecting all of these other objects out by Pluto, and it's actually an entire belt. So there's the asteroid belt in the inner system. There's what's called the Kuiper belt in the outer system. And Pluto is just one of these many bodies at this orbit. So it's just part of the Kuiper belt. Just like in the inner system, there's a dwarf planet called Ceres that is part of the asteroid belt. And we would never people don't argue that Ceres is a planet because they don't have this emotional connection to it.
Well, why do you argue that Ceres is a planet? Personally, I don't think we should discriminate against extroverts just because it's got a bunch of friends.
Sure. Well, then that would be if we did that, we would be expanding this kind of definition of planets, and we would be including things like Ceres and Haumea and Makemake and Eris. And so there'd be a lot more of them. And they don't really have like the same likely formation pathway that the major planets do, because like I said, they're not on like the similar kind of orbits and stuff. And so from a classification perspective, it makes sense for them to be in a different category. And so I think people get really attached to the idea of Pluto as a planet. It's sentimentality over science. And we should follow the science. I'm all about science. And science tells us that Pluto is not like the other planets. And so it's not, and I need to stress this, Pluto is a ball of rock and ice. Pluto does not have any feelings about its classification at all. So we're not hurting Pluto's feelings. And just because we don't consider Pluto a major planet doesn't mean that it's not interesting. It's still just as interesting as it ever was.
Why is Mercury, arguably the ugliest shithole of a planet, still a planet, but Pluto is not? Have you seen that colorized infrared from the New Horizons mission? Like,
oh my gosh, the New Horizons mission will forever be captivating to me.
Look at that absolute snack. Would you pick anything less beautiful to be a planet and not that?
It is absolutely beautiful. I love Pluto, and I love Pluto just as much as a dwarf planet, which is the categorization that makes sense. I think if Pluto did have feelings, I think Pluto would be happy to finally be understood in the proper context of the solar system.
I should clarify, all of these questions I am reading verbatim from my writer. Next, very scientific question about Pluto. Why is Neil deGrasse Tyson a coward who does not want to entertain the argument that this definition is stupid and linguistically challenged?
I cannot speak for Neil deGrasse Tyson, but I think I have made my opinion on why this is an acceptable definition quite clear.
I think specifically what Eris is trying to say is that planet should be a more inclusive term that includes exoplanets, dwarf planets.
I think the word that you're looking for here is world. So this is what we use the term world for. So things like the icy moons of Jupiter, they're not planets. They're obviously not planets, but they are worlds. And there's especially a lot of overlap here with like planetary science and astronomy. So planetary science is really interested in all of the worlds, right? And I mean, astronomy is interested in all the worlds as well, but we make more of a distinction between the different
kinds. Well, we call planetary sciences and it's worlds. Why don't we call it worldary science?
Sure, that doesn't have quite the same ring to it.
Doesn't. I have a question in my head. I guess calling it world science would be like geophysics. That answers.
Yeah. So there's lots of bodies that are worlds and that are very interesting as bodies, but they're not necessarily planets. And having these kind of definitions helps us be clear about what we're talking about.
So when you say you study planetary sciences, what you're really saying is you study bodies.
You study bodies of a certain size is what I would probably say. Oh, and fun fact, speaking of this, so you mentioned that one of the criteria for being a planet is that it has to be able to become roughly spherical under its own gravity. And there's a very fun term for this. It's actually called the potato radius. That is the radius at which something goes from being kind of a lumpy, like potato-looking thing to basically a sphere.
What is the potato radius?
So for rocky bodies, it's about 200 kilometers, and for icy bodies, it's about 300 kilometers.
That's cool to know. You have been very reasonable in your explanation of Pluto. However, you have not admitted that it's a planet. So my writer, Eris, would like to tell you, Pluto is a planet, and anything to the contrary will result in the need to cash Eris outside. How about that?
How about that?
Eris, I believe, is 5'1". You are 6'4", I believe.
Yes, ma'am.
And
so name the time and place, Eris.
Yeah, I think she's threatening you. And honestly, I'd like to see that because you are a naval veteran who is literally over a foot taller than her.
But I don't believe in violence, so we will just settle this with words. And my words are correct, obviously.
Thank you so much to Nora Bailey of Nora's Guide to the Galaxy and the University of Chicago's Astrophysics Department for joining us, telling us all about exoplanets. You can visit her YouTube channel and her website at the links below. Also, all of the things we mentioned will also be at the links below. Have a great day, and we will see you next week for another interview. Astra out.
Ad Astra, to the stars, to the stars.
Thank you so much for joining us here on Bad Astra. If you enjoyed watching, please like this video, leave a comment telling us what topic you'd like to see next month, and share it with everyone you know. Be sure to also subscribe and ring the notification bell so you never miss a new episode. And if you can't get enough of me, Eris, and Science Tommy, join our Patreon, where we post behind-the-scenes deep dives and other fun content. A special thank you to all of our Patreon supporters who make these videos